So hello everybody, thank you for braving the humid outdoors and security. My name is David Golden, I'm at MongoDB, and this is a talk about some real world optimization that I did there. I work at MongoDB, and I'm kind of curious, how many people have heard of MongoDB? Show of hands. Okay, everyone, great, fabulous. How many people have actually worked with MongoDB at any point in time? A few more hands, okay. How many people use MongoDB in their day job? One hand, okay, so I have some work to do. Fortunately, this talk has almost nothing to do about MongoDB except that it's something that I happen to be working on. So I'm responsible for a number of things at MongoDB. One of them is the Perl driver. I'm also responsible for a couple of other things. And the obligatory I'm hiring, and this time not just is MongoDB hiring, which I say at every conference and talk, but I'm personally hiring for my team. It's in New York. A lot of the work is predominantly around Go and some of our tools that are written in Go. But I would really, really, really love somebody with some Perl to help me with the Perl driver. So if you're interested or you know someone who might be interested, please come find me at the conference. So with that out of the way, on to the rest of the talk. So this is a talk about the real world and real code based on some work that I did a couple years ago when I was rewriting a lot of the innards of the MongoDB Perl driver. When I joined MongoDB about 3.5 years ago, the current driver was v0 point stuff. And this is what I now think of as the legacy driver. And I was writing the v1.x stuff, which is kind of the next generation that we have today. And the real problem with the legacy driver was that, among other things, it was incredibly, incredibly naive. It just sort of assumed that you didn't have to check anything for errors, right? Hey, I'm going to put something on the network wire. It will always succeed. You will never get an error putting anything on the wire. No problem. No error checks at all. A lot of the networking code is actually written in C. And so literally it was like C's networking functions, no checking to see if you got your -1 back, nothing. Just everything always works. It also didn't have the ability to fail over. One of MongoDB's strengths is the ability to have primaries and secondaries and relatively seamless failover, and the driver knew nothing about it. So for the next generation driver, we wanted to fix a lot of that and make it a lot smarter. The problem is that in addition to making it smarter and more robust, it also got a lot slower, significantly slower, like 50% as fast with certain operations. And that wasn't considered okay, even though we were being smarter and more robust. So we were kind of aiming for, could we get it to like 10, 20% slower would be kind of an acceptable degradation for actually like having a seatbelt when people are driving the car. So this talk is all about benchmarking and some of the benchmarking work that I did to optimize the driver and recover some of the speed that we had lost moving to a smarter driver. And so I have a lot of personal biases about benchmarking, and for the sake of our time, I'm not going to go explicitly into them, but I'll try to reference them as we go. I think one of the most important things about benchmarking is to try to isolate one thing at a time, and not try to test, like, I don't want to run like the entire test suite and see how it performs. I want to get down to like the small chunks of code and benchmark small chunks of code and all the things that they call, and kind of work my way methodically through the code base to try to find out what's slow and how to fix it. The other big thing that I believe about benchmarking is that we shouldn't trust averages or even medians or even any of the sort of like single point estimates of performance. I think what we really want is to be looking at distributions, not averages. The shape of the distribution turns out to be very important. You could have distributions with very tight bound around a metric, or you can have a very broad distribution around the metric, and you might care differently about the results based on the shape of the whole distribution, not just a single point. The other thing I believe is that when we're profiling, we should try to profile exactly as we're benchmarking. So I wanted to be able to run a chunk of code as a benchmark and then run that same set of code through NYT-prof and profile it and have it be the exact same execution both times. None of the existing tools are set up to do this, so of course I had to write my own tools. And I'm going to explain kind of what I wanted, and then I'll sort of go through some of the results and how I used it. So the goal is, initially, I want to load up some test data that I'm going to use. I'm going to set up for all of the test runs. For any individual test run, I need to do some prep work. I run the benchmark one time. I clean up after each run, and then I tear everything down at the end. Now, here at this first step, loading the test data, this is where I would vary the scale. So in this case, what I'll show today is a lot about insertion, single document insertion. So the scale is, how many documents am I going to insert? I'm going to insert 1 document, 10, 100, 1,000, 10,000. How many documents am I going to insert? That's where I vary the scale of the test. because performance also changes at different scales. Here, where I have sort of n and the arrow, this is sort of the loops. I want to do a number of loops, and this is how I'm going to build up the distribution of timing. I'm going to do this a lot until I have enough observations that I can get a distribution and start to look at what that means. The only thing I actually want to time, however, is this piece in the middle, running the benchmark. That's where I'm going to actually, I want to put check a timer at the beginning, check a timer at the end, and that's the time for that piece of work. That's also the piece that I want to benchmark. I only want to benchmark that single piece there. And then I'm going to collect all those timings to produce the distributions. So the tool I wrote, I'm just going to talk through the command line arguments briefly to get a sense of how I used it. This is all on GitHub, and it's very, very old, but some other stuff on cpan I'll talk about later. So I was looking at v 0.708.2.0, because 4-place versions are like all the rage. Those of you who know me know I have lots of rants about version numbers. I won't do them today. I was using a data set from Twitter, so I had basically go get twitter.json and load a bunch of data in. And this is my scale. So I was using 100 documents in this particular run, and I was running the metric for insert 1. So I had a piece of code which was doing that little bit of insertion as the benchmark. I'd then run that again for the current state of the repository. So I would use git describe to tell me about where I am in the commit history, and I'd use whatever I've built up into blib to run the stuff again. So now I can compare old versus new. And then I wrote a program that would just sort of dump this all into some charts. The charts look like this. The two on the top are actually for a find, and the bottom two are for an insert. For those of you who are chart pedants, you'll notice that this does not start at 0. I have some later that do start at 0 on the y-axis. But this is sort of showing how the distributions look. So I was using candlestick graphs, and this candlestick graph represents the interquartile range. So that I can sort of see, and I think so the big rectangle is the interquartile range, 25th percentile to 75th percentile, and the sticks I think were, I don't remember, 95th and 5 or something along those lines. So give me a sense of the spread of the distribution. And what I'm looking for is, are the distributions overlapping or not? And the more overlapping they are, the less confidence I have that the changes I've made are actually significant. This, however, gives you a sense of the starting point, that there was a significant difference between the old driver and the new driver. So having produced charts, then I want to move on to profiling. So the profiling looks like this. There we go. It's pretty much exactly the same as before for running the benchmarks, but now I put the profile flag on. And this invokes the NYT-prof and uses NYT-prof's ability to turn the profiler on or off. So one of the very first things it does is turn the profiler off. And then it runs all the code till it gets to that little bit of benchmark for insert 1, turns the profiler on, runs the benchmark, turns the profiler back off. So I'm collecting timings only around that little piece that I'm trying to analyze, and none of the other frameworking, scaffolding code around it. And then I crank the output through NYT-prof's HTML visualizer and look at it. And the first thing I saw when I started to do this work looked kind of like this. This is a flame graph. How many people are familiar with flame graphs? Some, but not all. OK. So as a quick refresher, flame graphs look really pretty, but actually only two things are significant. The depth of a call stack, so the vertical stack shows subroutines calling each other down into a call stack. And the width of any bar is the execution time, the inclusive execution time of that subroutine. Turns out the color is meaningless. It's colored to look like flames. I suppose you could color it to look like mountains or something else. And the left to right order is also meaningless. All that matters is you can see the call stacks, you can see execution times. But it does let you sort of see at a very large chunks of work that might be worth investigating. So in this case, a huge chunk of this work was all Moose object new and all of the things that it was calling. Imagine that. Imagine that. And then there's this other chunk over here, which is a whole bunch of stuff that boils down to coercing lots of values to tie Xhash. One of the interesting and I will say annoying things about MongoDB's document representation is that the keys and values have order. Order matters. And trying to get Perl to do that, particularly after Perl 5.18, randomized hashes gets very annoying. So the answer is slap lots of tie Xhash around things. But that turns out to be very efficient in certain circumstances. So this chunk in the middle is the part that's actually the insert 1 and is the real work. And it'd be really nice if I could get rid of a lot of the rest of it and focus on this. The next view I like to look at after the flame graphs is the profiler's listing of the top subroutines. People may be familiar with this view. And what's interesting about this is that this actually adds up all the individual occurrences of subroutines. So you could have a subroutine showing up in multiple places in your flame graph, And this brings it all together so you can actually sort of see which subroutines tend to be heavy. Not surprising, there's a lot of stuff which is related to Moo, and those who are very perceptive about Moose are very perceptive can see that a lot of this is class mop, meta attribute stuff. And this means that the Moose classes weren't immutable. So that's fixable by package meta make immutable so that we're not doing any meta object stuff once we're running. So great, freeze those classes down and move on. The other thing we could see from the flame graph, as expected, there's a lot of calls to tie xhash. Tie xhash ties hashes and keeps order. But as many of us know, tying is very, 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 very inefficient. So the answer is stop coercing to tie xhash. There were a lot of places where documents would get coerced to an xhash even when they didn't need to be, and just so that like the code could just sort of assume that it all worked in tie xhash. So I can always use the tie xhash API to work with stuff and not have to write it a number of ways. So if we stop coercing, we have to write more code to handle different cases of what people might provide, because some people might not care about order for certain types of documents and just throw it on in and it works. So once we make those two changes, have things gotten any better? And the answer is yes. So at this point, this is now mostly the insert one. It's mostly real work in the flame graph, and we can start digging into the specifics of what actual real work do we try to optimize. So going back to the list of top subroutines, we start to pick up some new things. So here we have constructors, and it turns out constructors are still kind of heavy. We make a lot of objects, and it's a lot of this was because the version 1 uses objects and roles on a lot of internal classes to be able to do similar things across different operations and adjust for the fact that MongoDB 2.4 has one wire protocol and 2.6 has another wire protocol, and now 3.0 has another and 3.2 has another. And all these little sort of operating or MongoDB version specific changes and roles make a lot of that really, really nice. And I don't have to write a lot of code, so it's easy to maintain. But we have a lot of these heavy constructors to think about. The other thing that popped out at me is that if you look closely, right, this is there's about, in this particular run, there are about 10,000 operations most of the time, but for some of them it was 40,000 or 20,000 or 30,000. And so we did a scale of 100 inserts across a number of loops over that to get about 10,000, 100 iterations of 100 inserts, we get 10,000 operations. Why are we getting things called 2, 3, 4 times the number of inserts? What's going on there? When I started drilling into the top function, this function called do timeout. Do timeout is a generalized sort of like select with timeout, either for reads or writes. Essentially just consolidates all of the do something with a timeout, wait for the network, but with a timeout in a useful way. And it looks kind of gorily like this, which I don't expect you to be able to read. But the interesting thing is, does everybody know how to read these, by the way? So I have like the left column is statements, and then how much time I spent on a line, how many calls there are, how many subroutine calls there are. Everybody knows that these things, NYT-prof. How many people use NYT-prof? Most of the room. Okay, so you're familiar with this at least a little bit. What's interesting up here is that, look at this, shows me where is do timeout being called. And it turns out that can read is calling do timeout 30,000 times, and can write is being called 10,000 times. Now I expect the can write to call it 10,000 times because I'm doing 10,000 insertions across the entire run. But can read has this big multiple. So why are there 3 can read calls for every write? Well, it turns out that one of them was this sort of approach of, we're going to see if the server's still connected. Before I try to do anything and send us something to the server, I'm going to check and see if that server's still there. I'm going to try to do a select to read and see if I get an EOF, which would mean the server has gone away, sent an RST TCP packet, and we're dead. Well, the problem with that is there's a race condition. There's a gap of time between the time I check to see if the server has sent an RST, and then I go ahead and send the write. It's very possible the server will have sent an RST packet right after I did the check. So since this is a racy check, it doesn't actually do a lot of good protecting us from network errors. We can just delete it. So then the other use is of the timeout is when we're reading responses from the server. So we send a write to the server sends back something that says, yep, got the write, it was applied, everything's okay. So why were there 2 reads for every response? And it turns out that the read algorithm looked like this. First, read 4 bytes to find the network length, or to find the document length of the response. And then read length -4 to get the rest of the document. That's a horrible algorithm. Here's a better algorithm. Read as many bytes as we can. hey, network, give me all the bytes you have. If it turns out that's not enough, we can go back and get some more. Great, went ahead and made that change. But then there was another problem. I started to test all this stuff because I made all the big changes to all the reads and the writes and all this stuff. So let me just start rerunning all this test suites and discovered that actually the tie xhash change I had made way back earlier broke bulk insertion. So if you don't want to insert one at a time, you want to insert like, here's 100 documents and insert them all at once. It's actually a lot more efficient because it's one network round trip. It turns out that something in the xhash change broke a whole bunch of stuff. And I wasn't running all of my tests after every commit. I was doing all this optimization. I was very excited, but I didn't rerun the full test suite and make sure I hadn't broken everything. I ran small parts of the test suite, but I didn't run everything. So lesson, always run tests when you're doing optimization. Make sure that nothing has broken every step of the way. So after eliminating the racy check and fixing the read algorithm, now we get something that looks like this. And the interesting bit is the do timeout has fallen down, at least a little bit. Still there, but it's not all the way at the top. And when I go back to my charts and I look at what kind of progress have I made along the way, it looks like this. So starting from the first all the way on the left is the original 0.708.2.0. And the rest are sort of incremental commits that I had made after some rebasing and all the rest of that. Wouldn't that Git rebasing with smoke testing been really useful for all that rebasing? Yes, it would have caught the errors. You can see that the things are sort of creeping up. It's also interesting to note that there's a lot of variance from run to run. Right? Some of these interquartile ranges are really tight, others of them are really long. Another lesson for optimizers is that while your tests are running, don't go and browse the web. Just get up, go away, get a cup of coffee. If you're in a startup, play ping pong or pool or whatever sort of diversions they have. Do sword fighting, on chairs, whatever you need to do to just leave your computer alone and let it run. But even still, there are some fluctuations that happen. And you can also see that there's actually a fair amount of overlap between the ranges, but they are sort of steadily marching upwards. And this is kind of what I was looking for, was not putting my reliance on any one metric, but looking to see if it seemed like the distribution as a whole was starting to march upwards. So what's next? I think I can actually slow down. I'm like blasting through these slides. So maybe the lightning talk as a warm-up is not so good for me as a speaker. So what's next? So now we go back and look at the top subroutine on the heavy list. Subroutines, it's encoding documents into BSON, which is the binary JSON document format that things get sent to MongoDB in. And when I start to dig into that, what I discovered is that there was a lot of one-by-one option overrides. So the BSON encoder class has a bunch of default options set, but you can also pass in a set of overrides when you do the encode. And what was happening was there was a loop running that for every single option that was possible, it would say, hey, check to see if this was passed in, go call the accessor on self to get the default value. Every single time, we were doing a whole bunch of method calls and a whole bunch of overrides. Well, self is a hash, so we can just let Perl merge them. So take all the defaults from self. If somebody passed in options, let Perl slap them all together. And then Perl's doing that down in the interpreter's C code and not through the Perl op tree. And this decreased the amount of time in the benchmarking from 849 milliseconds to 112 milliseconds. So a nice, easy win. And that moved the encode one way, way, way down in the call stack. It's still doing a lot of work, but now it's a much, much less work. So now let's talk about OO. And let's go back to that stuff I noticed very early on about heavy constructors. And when we're talking about OO, we're really talking about Moose, because Moose is extraordinarily heavy. So we had, at this point, with all the optimizations to date, still calls to new were very, very heavy. Well, and I started to look into what was going on. Well, in a lot of cases, the constructors had a lot of attributes with this. Is a string. Most of the attributes were string data. And the question is, do we really need this at runtime? Right? A lot of these were also internal classes. They weren't things that we were putting out in the library for end users to call. These were objects that we were constructing internally, private classes for our own use. How often are we going to mess up putting a string in where we not expecting a string, or putting some object that doesn't stringify where we're expecting a string? Not very often. We have a lot of control over it. So this is what I did. I got rid of the plain old check and replaced it with this ternary condition with assert. So if I set up a constant called assert based on environment, variable, whatever, then that check is going to be there. And otherwise, the check won't be there. So when I'm running tests, I can run tests with assertions on and make sure I haven't forgotten anything. I can also run it with it off to make sure that that still works. But for end users don't pay the cost of making sure that I know how to put strings in the right spot of my code. Easy win, and that drops the weight of the constructors way, way down in the call stack list. But the problem is it's not enough. We're still generating lots and lots of objects. I mean, to some extent, if I had to go back and rewrite this entirely from scratch again, I might even just get rid of a lot of the OO and just pass around hashes and avoid a lot of these overhead as well. And so I decided it wasn't enough, and that made me really start to think about Moose. So sorry, Moose, you're too slow, you gotta go. So the next change was to move to Moo, much, much lighter, and use class XS accessors to speed up a lot of the accessor calls to almost as fast as bare hash access. And that helped a lot, but I found the constructors were still doing a lot of work because we're still generating lots of objects, and even Moo has a lot of things that it does in its constructors. And so since these are internal classes, and since I know exactly what we're passing to them, we decided to cheat and create private constructors for our internal classes. And the private constructors were kind of like this. We created a role, private constructor, that we could add to whatever internal classes we had. And it used the MongoDB constants, which is where we set the with asserts or not. And if the asserts are on, we create an underscore new constructor, which just passes straight on through to new. So if the asserts are on, we get all Moo's normal checks. Did you pass me a hash, ref, or even number of pairs, blah, 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 all the usual stuff you'd expect. But if the assertions are off, then we just bless all the arguments that are provided straight into the class. Like, and Moo doesn't really care. Moose would have a problem with this. Moo, fine, it's a bunch of stuff. At worst, we've left out something that should have been required, or we've added in extra garbage values that aren't really attributes. But when we run with assertions, we'd catch that. And so this moves a lot of the work to the call site to make sure we have all these arguments. We're not using defaults. You can't use subroutines to generate attributes on the fly. If I need a hash reference, I can't say, oh, the default is sub, give me a hash ref back. I have to actually put it in the call site. But by moving the work to the call sites, I avoid all of the constructor overhead. And that makes things much, much faster. I also meant we could just put all the ISA checks back in. I don't have to with assert all the ISA checks because either the constructor is running or it's not, and that just streamlines the code a little bit to look at. So some other tidbits of things that we found to be useful. One of them is getting rid of try-tiny. Try-tiny is heavyweight. I think somebody has put a module out on CPAN that tries to reduce some of that overhead. Does that ring a bell for anybody? No? Okay. Try tiny, tiny. That sounds like something I should have written, since I like tiny modules a lot. So tiny, one of the problems with try tiny is while it gives you a lot of great sugar, it's also using lots and lots and lots of closures and subroutine references to do all of its magic, and those are heavy. Perl has heavy subroutine calls. It's just the way the language is. And so a simple eval block and checking the $@ is very, very, very fast compared to using try tiny. Try-tiny is protecting against certain problematic situations, which again, if you're careful and you know where your code is running and you're controlling a lot of this internally, you can actually sort of avoid it and you don't wind up needing try-tiny. So some things I used try-tiny for, particularly where I was getting things from users that I wasn't sure I could totally control. But other places we just got rid of try-tiny and went back to straight old eval, and that simplified things a lot. We also, within the Moose code and the Moo code, we're using type tiny, which is ironic because type tiny is enormous and not tiny at all. I'm not even sure what it considers itself to be an alternative to that it is tiny, because it is certainly not tiny. And coercions are expensive. So if you take some value and say, oh, I need to coerce this to another value, there's, again, a lot of subroutine calls. Is it the right type? If it's not the right type, do I have the right type? So a lot of logic happens to do coercions. So we tried to eliminate a lot of conversions and just get things into the right form very selectively where we knew we needed it. And that simplified things a lot as well. But also use time high-res a lot as a timer. I'm actually going to get us back on schedule. That's how fast I did the first half of this. Back in the back, I got the halfway mark sign held up. So doing even better than that. Time high res we use a lot for timing, and to get really good timing. So it's like, great, well, TV interval gives you an array that has the seconds and the fractional seconds, and there's functions to manipulate those and do those. The problem is, of course, that doing math with array components in Perl is slow, because we're doing array indexing, we're doing Perl's math, and what I found was that using decimal time and just getting time as a float meant that now I had a fractional time and a fractional time, and if I'm doing math on those, usually subtracting, to seeing like where I am in a timeout, Perl does that very efficiently because it goes, oh, internally I have a double representing that, internally I have a double representing that, goes through a bunch of checks to see if there's overloads, and then does it in one operation. And so it takes a whole lot of operations out of the Perl's op tree down to one operation, a subtraction on a scalar variable. So it turns out the decimal time, maybe not as ideal in certain circumstances, is actually a lot faster to do math with in Perl space. One of the other things I did was to cache Boolean true. So for those of you who were here early and saw me give my lightning talk about Boolean PM, Boolean.pm gives you true and false. These are constant functions that give you these singletons. Even though they're functions, there's still stuff that's happening. And Perl is not, in all cases, smart enough to optimize away those operations. And so I found that in certain cases, just calling that once and caching it locally and just dropping it in everywhere was helpful. I think possibly the reason it wasn't optimized away is because we were calling them from excess code. So if you're calling from excess code, it winds up having to do the function call anyway. Perl can't optimize the op tree. So caching all these true and false values once in a way that we could just drop them in without a function call turned out to speed things up. Caching the primary server between topology scans. This requires a little bit of explanation, which I was going to skip, but since I'm ahead of schedule, I'll explain it. So MongoDB operates in a mode we call replica set, where you have a primary server which takes writes and where you should do most of your reads, and secondaries which are getting replicated copies of all the operations and can step up into the primary role if the primary goes down. And every so often, the Perl driver has to sort of stop and check the world and say, hey, make sure I know who all the primaries and the secondaries are. If somebody has added secondaries, I need to know about it, and kind of gather the view of the world. And there's a lot of logic, a whole specification for how we choose a server. It says, oh, I need to do a write, so go to my set of servers and see which one is the primary and all this stuff. Well, all that logic is irrelevant in between changes to checking the topology, because if I found the primary one time, it's going to be the same primary. I can cut out a lot of the selection logic by caching the choice until the next time I update the topology. So we cached that. There were a lot of invariants were cached. A lot of these invariants were things that had to do with does the server support a certain feature? Is it a version 2.6 server? Is it a version 3.2 feature? And instead of doing a check every time of go get the server version and do an equals or greater than or equals operation against some value, turn that into a Boolean value and cache the Boolean value. So I'm only doing the comparisons one time. That helps a little bit. So the general message is cache stuff. Anything you can do to avoid Perl having to do computations will make hot parts of the code faster, because Perl operations are relatively slow. Another thing I stopped doing was stop checking for fork or thread spawn. So if you have a network connection and you fork or you spawn, generally speaking, you get that same network connection open on the other side. And you need to close it and reconnect when you're on the other side. Well, in normal operations, you're not forking and spawning. And so like every time I insert a document, oh wait, did I fork? Okay, let it go. Insert another document, oh wait, did I fork? No, let it go. It's silly to do a fork check or a spawn check for every single insertion. You make people pay a cost for that safety on every single insertion when it's actually pretty rare. So instead, we move the cost of that check to the user and say, if you fork or if you spawn, it's on you, the user, to reconnect. And there's a method you can call to say reconnect to all the servers, and it drops all the connections and reconnects, and it's safe. And that gets rid of all of that. And I think that's kind of a general lesson around, if you can, don't check for rare errors all the time if somehow they'll be caught later. Even if somebody does forget to reconnect, they're going to have problems because you're going to have two sides of a fork trying to talk to a server at the same time over the same socket, and you're going to get errors because you'll get gibberish. So if people make that mistake, it will get caught from the gibberish. So we don't need to be checking for rare errors if they can be caught later. So moving a lot of error checks out of the tight loops, as long as somehow they'll get detected later on, helps. And this is generally sort of another thing in optimization is, there's a lot of things we do for safety. Make sure, is the var given value what I expected? All of those checks add up. And so if you can control them and get rid of them, that's really helpful. So then we get into stuff with some really, really marginal benefits. And I agonized a little bit over whether I should even be doing these, because they start to get really ugly and probably controversial, and probably half the people in this room will probably be revolted by even what I'm suggesting. Nevertheless, like I did find, again, looking at distributions and looking at all those timings, I was still getting some marginal benefits in performance by doing this. So the number one thing is avoiding scope, right? So every time you create a new scope in Perl, the Perl interpreter does a lot of work to set up that scope and get ready to clean up that scope at the end. So things like this. If some bad condition happens, throw ouch. Throw ouch is sitting inside a scope. So before it can do that throw ouch call, the Perl interpreter has to set up all the mechanisms it needs so that whatever happens in that subroutine can be cleaned up at the end of that block. Right? If you'd created variables, they'd have to be garbage collected at the end of it. So all of that machinery gets set up simply so I can throw a method. So the answer to that is just use postfix if. Throw if condition. Gets rid of the scope, same effect in the code, but no more scope. And it turns out if you have enough of those in a hot loop, because you're doing lots of error checking, again, they add up. Similarly here, if else, if the server version is greater than 2, do something, otherwise do the legacy version of stuff. You just turn that into a ternary. Same effect in the code, no additional scope creation, no additional cleanup creation. So, what? So the idea is you can uglify your code, make it a little harder to read, a little weirder to read, but if this is in a tight part of the loop and you're really, really concerned about performance, you can actually start to see some marginal benefits. You can avoid intermediate variables. I like intermediate variables for readability in certain circumstances. There's a great book, I think it's called The Art of Readable Code, that has some really good stuff on when to use intermediate variables and when not to. When does it enhance readability? When does it detract? But intermediate variables require some sort of memory allocation, some sort of copy, and then you use them again. Things get copied around a lot, so you want to avoid those. This is really one of the most startling things that I discovered actually helped. Avoiding statements. And what I mean by that is avoiding semicolons. So here at the top is a bunch of assignments. Assign this, semicolon, assign this, semicolon, assign this, semicolon. I said half the people are going to be revolted. Sawyer's over there like with his, Sawyer's in the corner like this, just with his hands in his face that I'm saying this. When Perl sees a semicolon, this is a time for the Perl interpreter to do several things. Hey, have any signals fired? Hey, is there any memory that needs to be cleaned up? Have any reference counts gone to 0? Every single semicolon is an opportunity for the Perl interpreter to do work. It's yielding time back to the Perl interpreter to say, hey, do anything you need to do. This is a good place to go do that. Well, in this case, this is just a bunch of assignments. By wrapping the assignments in parentheses and throwing them into commas, all the same assignments happen in the same order, but without all the intermediate checks. And for 3, maybe this is ridiculous, but there's a lot of places where you might actually have like a whole bunch of things being assigned in a row. And if you replace all those by commas, lo and behold, you actually still see, in a tight loop, marginal benefits by not letting the Perl interpreter check for a bunch of stuff that probably hasn't happened. So is all this working? And like I said, really marginal benefits at the end, but I had a boss who was like, this should be like, no more than a 10 or 20% degradation. So I would keep chipping away. And the answer is yeah. Like you can actually win by hitting singles, right? Enough little increments, and you can see how many different little changes I made, right? Bit by bit by bit, marching up the performance curve to the point where in the end, yeah, it was about a 20% performance hit, but a 20% performance hit for a driver that was a lot smarter and a lot less naive about handling errors. So this is the evolution of the flame charts. Top flame chart was the first one I showed, where you've got a big block of mousse on the right and a big block of coercion on the left. The middle one was after getting rid of those sort of non-work related sort of hits. And the final one was after really streamlining all the work and moving to mousse, getting rid of a lot of nested calls, a lot of coercions, much, much flatter. And at that point, when I looked at the top subroutines, this is what I saw. The very top thing is core select. That means that the biggest amount of time in the program in one spot is sitting there waiting for the network. And this is waiting for the network on a benchmark that I'm running on my laptop. this is the best possible situation for minimized network latency is talking to localhost. So all I'm really doing is waiting for the server on my laptop to do work and give me the response back. So at that point, I said, I think I'm done. like in a real world application, right? So like this is clearly inserting a whole bunch of documents one by one is a very artificial benchmark. And I went through and I did this for insert one, insert many, update one thing, delete one thing. I went through all, find one thing, find lots of things. I went through all the different major parts of the code, ran very specific benchmarks. And because a lot of these cleanups were global, by the time I'd done insert one, a lot of the other stuff got faster. But there was incremental benefits all the way through. When I got to the point where I said, look, at this point, most of the time is spent waiting for the network. In any real-world application, the network is not going to be local. It's going to be remote. And any application is going to be doing actual real work. On top of this, I said, we're done. So that was the point where I declared success. A lot of this code I had written, and it was all sitting in like a GitHub repo that I use for like scratch work. I did take a lot of the benchmarking code, the sort of the, go through all these steps, run just the one piece, be able to profile just that one piece. And I released that to CPAN. It's called Benchmark Lab. I call it a work in progress, except I haven't worked on it in quite a while. It doesn't do any of the graphing, doesn't do any of the charts, but it does give you, it doesn't do any analytics on the timing, but it does give you the facility to do the sort of setup, run a bunch of stuff, benchmark a piece, profile a piece, and give back the whole bunch of timings. And it makes it very easy to sort of write stuff against it. So if people are interested in this technique, I encourage you to look at Benchmark Lab, contribute, do other things with it, write cool stuff, give talks, and so on. So with that, I've actually almost pretty much got us back on schedule. Woohoo. Are there any questions, since I went through things very, very quickly? Yes? Oh. I think I might like change my routine of like, instead of having a question slide, I'll have a thank you slide, and then everyone can applaud, and then I'll go to questions. So questions, yes? So you remember the do timeout call? So do timeout is trying to give a very bounded time for how long we're going to wait. And if you do this correctly, you have to actually account for the fact that you could have a interrupt, EINTR. Somebody know what that stands for, long form? So anyway, it's possible for you in a select to get an error back. And the error is simply your operating system had to interrupt this operation, and it didn't finish. And so at that point, we don't want to throw an error. We want to restart, but we don't want to restart with the same timeout we started with. We have to restart with a smaller timeout. And so all this stuff is sitting in a loop, and we're using time high res to sort of figure out what time was it then, what time is it now, how much time is left to tell select to wait. So it turns out actually we're using a lot. Other questions? Bulk. You're going to criticize all this stuff, I know. What is it? Yes. It's true, but that's why we have the timeout. So, but the problem was that the read was actually saying like, please read just 4 bytes, instead of saying. Yeah, absolutely. Yeah, and a lot of this stuff also accounts for the fact that if you're using an SSL connection, you can't actually sort of do a select because you need to actually check to see if there's stuff that the SSL frame has already received. So there's a lot of complexity to this, but the ultimate insight was we wanted to say to the network, give me everything you've already received, because maybe that's enough. Maybe the entire document came through because the whole document was 100 bytes instead of just asking for 4. So now the reads are, give me up to 8,000 bytes. Whatever the network gives you back, then check the length on that. And if it turns out that the document needed more than that, then we just do more reads. The idea was get as much as we can in one shot because the network probably already has it. Yes? fortunately or unfortunately, as the case may be, the MongoDB wire protocol is synchronous, so it's send one message, get one reply. It's much like HTTP in that sense. This is like, if you imagine like, I'm going to read an HTTP reply, and instead of reading the whole reply, you read like the first few bytes, do some thinking, and then read the rest of the bytes. So we don't have that particular problem. I did discover a bug, which was the code didn't actually, so I'll own to this, it's my bug. The code didn't actually account for the fact that you might just receive less than 4 bytes. Hey, give me 4 bytes, and it says, here's 1. So actually, now there is stuff to say, oh, well, if you gave me less than 4, now I have to actually go and try to get to 4 and figure out the length to read the rest. And it happens very rarely, but networks are funny. You can get all sorts of crazy stuff. Other questions? Yes. I did not. I sort of am of the mind that in the modern day and age, memory is memory, and if people really care about memory, they're probably not using Perl in the first place. They're probably writing it in C or C++ or something where they can control it a little more. It wasn't a major consideration for us. Mostly it was about speed, because MongoDB is advertised as being fast, and that's the thing that most people, if they see a degradation, we're going to hear about. I got a sign which said one more question, but I want to actually take one more question because I did such a great job catching up. So you had a question back there.
I just had a question about
Benchmark Lab, yeah. No, because the timing is only around a small bit of code. Yeah, I think this is not something I would recommend in almost any circumstance. However, how many people have bosses who ask for unreasonable things? Some people in the room. Okay, so when the boss says this has to be as fast as possible, you start looking for everything you can possibly find. All right, thank you all very much. I think we're roughly close to time, and I will see you all around the conference.